Hi, this is Larry Benko, W0QE, and this video may be one of the most valuable videos I have done if you plan to build circuits that will be operated at power levels beyond a few hundred milliwatts. Doing an analysis to determine the maximum stresses on every component in a design is what separates engineers from hobbyists and will give you pride and satisfaction in what you build. Finally, the process to make these calculations is quite easy to do in SimSmith and should be in your SimSmith bag of tricks. Being able to determine the maximum voltage and current in all the components of a circuit, particularly if it's a higher power circuit, is incredibly important. SimSmith can help us do this, but there's a number of steps we need to take in order to get a realistic answer. You don't want to size the components too conservatively, and you don't want to blow them up either. So with that in mind, I outlined 5 different steps to take. The first step is design a circuit, and I don't think that's part of this video, so I'm going to start with the circuit I already designed with some artificially created problem I wanted to solve, and I'm going to go through then how to determine the sizing of those components. So to begin with, I built this filter. It's a low-pass filter, two parallel capacitors to ground, an inductor in the center. It's a pi filter, and this inductor is resonated. Now what that does for me, it's a 40 meter low pass filter, but this is a resonant trap on 15 meters. And the hypothesis here for my design was that I like 40 meters, and when I'm on 40 meters, my next door neighbor or close neighbor, who is also a ham, he likes to use 15 meters, and he hears my 40 meter transmitter phase noise on 15 meters. And it causes him not to be able to hear people. He cannot get rid of my phase noise. My phase noise is actually in the spectrum. He can't filter it out. So I have to get rid of it. So I built this filter, and let's look at what the performance of the filter is. Here it is. Again, there's the picture of the filter. I just cobbled together a pi filter, then put a capacitor in parallel with it, adjusted the inductor while I was changing the capacitor, and it's pretty easy in SimSmith to do this. If people don't understand how this is done, I can easily do a couple videos on just coming up with filters on your own. You don't have to use any kind of a program to do it. It takes literally like just a couple minutes to do. I came up with this filter. I made these 2 capacitors be standard values, 470 picofarads. I took the resulting inductance that I got after I messed with the capacitor that resonates it and picked this number to be a little bit even, and this turned out to be what it turned out to be. Now, all these parts have tolerances on them, of course, and stuff, but that's not the purpose of this video again. The purpose is to calculate the voltage and currents. If this inductor is 10% higher in inductance, it's not going to change the voltage on it only about a few percent, so it's not that big a deal. So what I say here is 7 megahertz passband that shows 19.9 dBW. Well, it's a 100 watt output, so that's 1/10 of a dB passband loss. I see SWR in the passband. If I expand this scale again, my 1-to-1, there's below 7 megahertz, and there's above the top, below 40 meters and above the top of 40 meters is all better than 1.1-to-1 SWR. And if I look at the notch here, here's 19.93 megahertz, here's 23.3. So the 15 meter band is definitely contained within this notch, and this is 10, 20, 30, 40 dB down. So my phase noise will be reduced to my neighbor by 40 dB. And the assumption is he hears it like maybe S5 now, so 40 dB will put it down in his noise level. So this is a, it's not a real problem, but it represents the problem that somebody might want to do, and it represents a chance to go through the motions here on how to do it. So that was step 1. Step 1's done and out of the way. We will come back to this circuit in a little while. Step 2 is to determine a range of loads for the circuit. We don't want to necessarily operate this circuit into every SWR, every impedance in the world out here. We're not going to do that. And if we did, we'd have components that would be sized inappropriately. They'd be too large in most cases. So we should determine what is the reasonable range of the load for the circuit. Then we need to determine the type of generator we're going to put into the circuit. And then SimSmith can do the analysis very easily. And when we're done, we're going to look at how we can determine if a part meets the calculated voltage and current requirements. And in some cases, you can get that from data sheets. In other cases, you need to do it with some testing. And this is aimed at the testing piece of it if you need to do it that way. Step 2 is to determine a range of loads for the circuit. And the choices could be things like all impedances, a single impedance only, SWR is less than a certain amount, SWR is less than an amount with full power from the generator, SWR is greater than that amount, than the full power amount at some reduced power, or some other restricted range of impedances. Generally, bounding the impedances by SWR is the best thing to do if transmission lines are used to connect to the actual load. And hopefully that's kind of obvious, but let me just do that here in this circuit. If I had a generator that had a 25 plus J0 load, an antenna that had a 25 plus J0 load, and I had a piece of transmission line in series with that, the impedance I would see at my transmitter would be somewhere along this circle. Now I've made this transmission line have virtually zero loss so that when I wrap around here I don't see the spiraling inward effect that you get with loss. But all these impedances along this circle represent 2-to-1 SWRs. And all of those are equally likely on a random basis to be the impedance that our circuit under test will see. Now, if we knew exactly what length transmission line we were going to have because we had a captive system, we could obviously do a different type of calculation. But in general, when we don't know the length of transmission line, we include all those impedances. And the goal here is to do something where we sweep a parameter over a range, and I have 2-to-1 SWR everywhere, and I would have a power everywhere of 88.9 watts. And that difference between that and 100 watts is the mismatch loss. But when I plot the voltages and stuff across the components in our circuit, this will be at a certain length of transmission line. It'll be like the dot on the dot here will be the point as if I had this in the circuit. This would be the voltages and currents I would see with a 4.935 foot piece of transmission line. And this works pretty nicely. It turns out that I didn't use enough length of my. Actually, I needed more like. Okay, we need 46 feet. The voltages and currents that the components see along this circle are larger than they are for smaller SWRs. And you can prove that when you build your final circuit, because all you have to do is just change this SWR and make this circle be smaller and look at the voltages that you get on the square chart and the currents, and you'll see that they're always smaller than they were for the higher SWR. Now, what if we don't want to have a circle that's centered here? Maybe we're driving some, I don't know, let's suppose we're driving some kind of another amplifier and it's got an input impedance of, say, 10 plus J12. It's got an impedance in a range of, say, around 10 plus J12. In that case, we can offset this circle pretty easily. We can do that a whole host of different ways. We can pick an impedance here and we can have a piece of transmission line that wraps around it. Or we can do something like this circuit right here does, which is a piece of transmission line of some impedance and then just an LC afterward to move it around. And let's see if I can get that up somewhere up around the 10 plus J12 area. Well, this turned out to be lucky. Now, if that's not quite a big enough area, I can just change the impedance of my piece of transmission line and tweak on these just a little bit. A little bit more, say, and center it. Now, this will be the range of impedances that my circuit sees as I sweep along as I change the length of my transmission line. So this whole conglomerate of components would represent the new load. But that gives us a way to put various load impedance ranges against the generator. You can do it other ways too. In an earlier video that I did on harmonics, which I think was video 22, I think the next either that video or the next video afterward, I dealt with, or maybe it was the video before that, was dealt with creating a bunch of artificial points throughout the Smith chart. And you could manually create those in some kind of an editor and just put them in a file and read them in too. But this works out quite easily. Step 3, determine the type of generator or transmitter that we have, the power level, and optionally the duty cycle. Now, SimSmith cannot take care of the duty cycle, but the duty cycle is something you can keep track of. And if the duty cycle is short enough so that the components don't heat and cool during that on-off duty cycle, you can use that in the final step to adjust your current that the components need to be rated for. So let's look at that for a minute. Generator types could be things like a true use Z0 generator with a resistor. In that case, you have a voltage source here you can think of as an ideal voltage source in series with a resistance. In this case, it'd be 50 ohms, such that half our voltage would be seen here. The power here, which would be, in this case, it's 0.88 watts, would also be the same power here, be 0.88 watts. And that's good for a signal generator and maybe some low power type amplifiers. Additionally, we have like what I'm calling an approximate use Z0 generator. And that's kind of what you get in a regular RF transmitter, where the output impedance is determined by the voltage and current limits on the amplifying device and then LC components afterward, such that the maximum power occurs at the 50 ohm point if it's designed for 50 ohm output impedance, and any other impedance, as we get away from that, the power drops. It may not drop exactly like the UZ0 generator does, but it drops pretty closely. And that's a good approximation for a lot of transmitters. Most of our current day transmitters fall in the X-match generator category because they artificially hold the power up until you get to a certain point in SWR, and then they let it collapse. And any circuit that has an output matching network that's adjustable or microprocessor can do those kinds of things. So, but you have to be careful with an X-match generator in that it'll deliver power when you have incredibly high SWRs. And if you look at a filter through with an X-match generator, the response to the filter won't be appropriate. So remember, the X-match generator is only an X-match generator over a range. And then after that, it crumbles. So for this example, what we're going to do is we're going to use a 2-to-1 SWR at 100 watt level, and I will set my generator type to be, for the moment, a use Z0 of magnitude 100 watts. I could have put the 100 here in the power, in place of the power, but by putting the PWR there, it generated a variable called PWR that's a parameter, which I can then roll my wheel and change the power. Notice how this is a 2-to-1 SWR, no matter what the SWR is 2-to-1, no matter what the length of the transmission line is, and I always get 88.8 watts. That's the mismatch loss from 100 watts. If I made this be a 3-to-1 SWR, this will drop to 75 watts, which is the mismatch loss, or 1.25 dB from 100 watts with a 3-to-1 SWR for a for UZ0 generator. If I change this to next match generator, of course it goes immediately to 100 watts. Now that we have the generator and the load figured out, let's let SimSmith do an analysis of the voltages across all the components and the currents through all the components in our circuit. What we need to do is bring our circuit back into the circuit we want to test here into the bigger overall SimSmith circuit. These two components are the load. This is the generator, and we've decided that 100 ohm or 2-to-1 SWR, all phase angles produced by changing the length of the transmission line, are going to be the load for the circuit. The generator will produce 100 watts into a 2-to-1 SWR. So X-Match is a good generator for that. We will not let this go any higher than 2-to-1 SWR, and we'll see what we get. Now, we could have built this circuit in discrete components over here, discrete blocks, in which case we would have had to have plotted the voltage and currents by going to the plot window and remembering the syntax, or we might have been able to read them off the windows here as we manually change the length of the transmission line. But it's a lot easier to do now in version 16 with the ruse block. And the ruse block now is getting to where it's going to become probably the default way to do a circuit because of this type of stuff. When we right click on any component, we get a list of things that we can plot. And small v and small I are current through the component and voltage across the component. Actually, in the case of a single component in the ruse block, large V and large I give us the same answers. But small v and small I are by old standards the appropriate ones to use. We can do that for all four components. Small v, small I. Now you'll notice we have 8 new plot things here. And the plot window is still empty. These were just artificially put in here somehow, but that saved us a lot of time for what we would have had to have typed before. So now let's get rid of this. And we look at all this stuff. And let me even make it more complicated for a moment. Let's put the power to the load in the circuit. And since it's 100 watts, that's definitely wrong. There's our power to the load. And let's put SWR here. We see it's pretty much 2-to-1. It varies a little bit, though. It varies a little bit due to this circuit, but it's pretty much what we had on the output is what we have on the input, but the phase is completely different. But what I wanted to show was there's lines underneath of all of these titles up here. The solid line, which is the blue line here, solid, it's SWR. The dotted line, the small dotted line, is the Y1 axis, which is V. The large dotted line is current, that's this one, and the medium dotted line is power, that's this one. They're a little tough to discern sometimes. And if you can't figure those out, like if the power one got a little bit confusing with the current, I can just right click on this thing and say, give me a new color, and off I go, and now it'd be a different color. So there are ways around that. There's only so many colors available by default in SimSmith, and then it recycles the colors. If you go and you right click on on what you want to plot, you can pick lots of different colors, although at some point in time they become hard to tell them apart. So we right now have 8 plots up here, 4 are voltage, 4 are current. And let's look at these individually because in total they're probably a little bit tricky to tell them apart. The red curve is the voltage across C1, and we see that going to just about 100 volts. And it is 2.0, let's call it 2.1 amps. So it's 100 volts and 2.1 amps. C2, the voltage is just about exactly the same as C1, except that the phase angle's different. It's pretty much a little bit less current, not much though. And again, it's pretty much 100 volts, 2.1 amps. The inductor, the voltage across the inductor is higher. If it's an air-wound inductor, we don't have to worry about any kind of flux issues. If it's going to be something we wind around a toroid, we need to make sure that the 142 volts RMS is not something that will cause saturation in our toroid. And clearly capacitor C3 will have the same voltage as the inductor does because it's in parallel with it. And its current will be something pretty small because it's a small value of capacitance. It's actually not that small. It's actually higher than the than C1, C2. Oh, it's got, well, it's higher. Okay. So no, that's the inductor current. I'm sorry. The capacitor, we didn't have, here, it's lower. It's a small value capacitance. The voltage is a little bit higher, but it's a lot smaller capacitance. It's nearly 10 times as small. So that makes more sense. So C3 sees 360 milliamps basically and 140 volts. But for sizing purposes here and for discussions, let's look at C1. So we're going to say C1 needs to be 100 volts and 2.1 amps. If our transmitter had not been an X-match type, but had been a UZ0, so that the microprocessor didn't artificially let the power stay high for 2-to-1 SWRs, this would have dropped down to 93 volts and 1.97 amps. Not a huge difference, but it would have dropped down. Likewise, if our circuit was a 50 ohm circuit, we would have sized these components at 70 volts and 1.48 amps. So we see an increase from 1.48 amps to 2.1 amps. That's roughly about twice the power. It's about 1.4 times the voltage, or excuse me, 1.4 times the current. So it's 2 times the power because power is current squared. So these capacitors would have twice the power in them than what you would normally think if you hadn't done this analysis. In some circuits, it can even be more than 2 times, depending on the circuit and stuff like that. But it's something you need to consider. The other thing is, if we had a generator that had a large amount of harmonic content in it, we would need to account for that. I did that in video number 22 on harmonics. The output of a solid-state amplifier will have the third harmonic be down maybe 12, 13 dB. A 12 dB down harmonic is 1/4 in amplitude of what the fundamental is. That will significantly change the current, particularly of the components near the generator side. As you get out on this side of the circuit, the third harmonic will have been filtered away, so you won't see much change. But this first component will see a significant change, and that needs to be accounted for in the generator. Again, that's in video number 22. But this is the result. The other thing I wanted to do real quickly is go back to 100 ohms here. I made the comment earlier that the voltage we see here, and let me put a line right there, and I'll change the SWR, make it lower. Notice in all cases, no matter what the phase angle is, it's less than what it was at 2-to-1 SWR. So you don't need to check all the points inside. You don't need to check all these points. By going around the outside, completely around the outside one time, you have captured all the maximums. And now for the final piece. We have determined the maximum voltages and currents on all our components, and now we need to determine whether or not a part that you might have on hand is adequate for the job. If you buy a part and the data sheet is clear as to how much current the part can handle, you're good to go. But if you have parts that are laying around, you might not know how much power they're able to take, and you might not know how much voltage they're able to take too. And you can build circuits, and SimSmith can help you, that will allow you to test these components. Let's, for an example right now, let's use the example of C1. It needs to be a 2.1 amp current we need to put through C1. I'm assuming that everybody owns a 50 ohm dummy load resistor. You clearly own a transmitter. And we're going to leave the transmitter in the UZ0 mode right now for the moment. We're not going to count on it being able to match any type of wild impedances out here. If we were to put our 470 picofarad capacitor that we needed for C1 in this circuit, we would see that our transmitter can produce 1.28 amps. That's not 2.1. That's not enough. Even if we turn on the tuner in the transmitter, well, maybe we don't. Let me move this out of the way. Bring the Smith chart back up here. This SWR is over 2 to 1. So I'm going to assume that the transmitter no longer is putting out full power. So maybe we've got a transmitter that's got a tuner in it. So if we put the tuner in there, we can go back again to the X-match mode of doing things. And we've got 100 watts here, but now we have a total of 1.4 amps. We still need to get up to 2.1 amps. How can we do that with a 100 watt transmitter? And it turns out it's pretty simple to do. There's a lot of different ways to do it, but one of the simplest ways is to lower the impedance in this circuit, match to the generator, and keep on going. We can do that a couple different ways. You obviously have a 470 picofarad capacitor that we're testing. Why not put a couple more in the circuit? Let's put them over here. Before I do that, let's change this guy's name. Let's call him Test. So that's the one we're trying to test. I'm going to put a capacitor here that's 470 picofarads also. And I'm still putting 100 watts into this circuit. We'll worry about later on about the fact that this SWR may be too high for this matching network to work. But now notice that our current has risen to 2.07 amps by dropping this impedance. Well, I can clearly put one more in here too. Control C, Control V. We'll put another circuit, another capacitor in here. And now my current through this capacitor is 3.35 amps. More than I need, and I can drop the power down to get to my 2 amp number quite easily. However, the SWR now that my transmitter sees is pretty high. I could build a circuit that matched it. If I own a matching network, say a T-tuner, I'm going to put an L network in here, but let's just assume I owned a T-tuner or something else that was good for the power. I could put that in there. My transmitter would still put out 100 watts no matter what into this good SWR. I'd have a little loss in this circuit. I would see over here on the load, my watt meter over here at the load would see 94 watts. And 94 watts I would have 3.27 amps. So what I need to do is back this back down till I get to 2.1. Call that close enough. 2.1 amps. This is the component we're trying to test. So I haven't built anything yet. I've just got this all set up, ready to go. So when my watt meter reads 39 watts, then I have 2.1 amps through my component that I'm trying to test. And it does not matter how much loss this circuit has. This circuit can have huge amount of loss because we're measuring the power out here. So we don't have to worry about losses in inductors then. And what we're going to do is we're going to turn our transmitter power down, and we're going to tune up into this circuit, match this network here, or T-tuner or whatever. We've got Pi tuner, we've got a L network. It doesn't matter. We're going to match it to the transmitter for low SWR. Then we're going to crank the power up a little bit, and we're going to measure the temperature of this component. And most components are rated for some number like 85 degrees C or 25 degrees C or something, 105. But the lower the temperature of the capacitor is, the more reliable your circuit will be. You can decide what's convenient and what's not. I usually paint the parts with indicating paint that melts when it gets to a certain temperature. It turns out that I was having a discussion a few weeks ago with a guy, and he told me that you could use crayons for some of this stuff. So I went to Crayola's website, and Crayola's website, apparently a lot of people are using regular Crayola crayons Not the glitter ones, not all the funky ones with the that are odd or anything, not the metallic ones, but the good old, 12-pack or 8-pack that's got black, yellow, green, red, nice vibrant colors in there. They all melt between 120 degrees and 147 degrees Fahrenheit, with the yellow being the highest one at 147 degrees, plus or minus a few degrees, and the black one being the lowest at 120. You could obviously do your own tests with boiling water or heated up water and a thermometer to see where they melted. But you can take this and this capacitor here, put some crayon on it, and see what current it takes to melt the wax. If you were to put a component in here that handled the 2.1 amps and was still lower than 120 degrees Fahrenheit, which would be 49 degrees Celsius, this component would last forever. So you start off here at low temperature, you crank the transmitter up a little bit, crank the transmitter up a little bit, keep cranking it up, and pretty soon you get to a point where it melts. And if that point is before you get to the 2.1 amps, you've got to decide whether you can actually go to a higher temperature or not. But capacitors are probably the most unreliable part we have in circuits these days, and particularly like ceramic capacitors. Industrially, when I solder them onto a circuit board, particularly the surface mount ones, I heat the circuit board up at the same time I heat up the surface mount parts. They both expanded at the same time. When we hand solder them, the circuit board is generally cold, and that's due to a lot of problems you have with the end caps breaking on capacitors. So one thing that's important to do here is if you're going to use surface mount components, is to heat the board up, or just don't have the part get very hot. If the surface mount components are cheap, use a few more of them so they don't get very warm. But again, this is all part of of engineering something to last. But this is a good way to use a small, lower power transmitter to test current higher than the transmitter normally could put out by the application of a network that matches it, and then a low impedance out here. And you can do a corollary to this where you can get higher voltage here than the transmitter is capable of putting out also, and test for voltage breakdown. Testing for voltage breakdown is destructive. If it passes the voltage requirement that we need, which was the 100 volts RMS, or 141 volts peak, you'd probably want to test it at twice the voltage at least to feel comfortable. But this is ways that SimSmith can help us build circuits that we can become happy. You're proud you built the circuit, and you're happy with the results, and you feel good about how you did it, rather than just glomming the parts together, being done, and hoping that every time you turn it on, everything works. I hope you've enjoyed this video. It's been a little bit longer than a lot of them are, and if you like it, give me a thumbs up, please. Tell people about these videos if you think they'd be interested in them. And if you haven't subscribed already, please subscribe. Thank you very much.